Hey guys, I wish I could be there to help you see this three-dimensional stuff, at least on the first day. Do the best you can, because sometimes like my hands are going to be all in and out of here today because I want to describe stuff to you and I can't because they're not there very well. So do the best that you can, and we'll try and clean things up tomorrow, not Friday, and then next week. So if you're a little bit fuzzy on it today, that's okay. Sometimes it takes time to get this volume stuff through. All right, we're going to start off with area. Just some basic background information on area, stuff you already know. Area is the amount of flat surface enclosed in a figure. It's the number of square units contained. In that figure. So remember when you first started doing area, you counted up boxes which were inside. In geometry, you found area of triangles, of parallelograms, circles, trapezoids, etc. And you did all of that by using formulas. In calculus, we took this one step further and we said that we wanted to find the area underneath a curve or underneath a function from A to B. And the way that we found this area in here, that area is summing an infinite number of rectangles, the integral from A to B of f of x dx, where this f of x part in here, that represented all of the heights, and this dx represented those very, very tiny widths. And this whole thing together summed an infinite number of rectangles. Volume is the amount of three-dimensional space enclosed in a figure. It's also the number of cubes inside of a three-dimensional shape. All right, in geometry, you found volumes of prisms, boxes, of pyramids, of cones, what else did you find volumes of? Oh, spheres, and cylinders. How did you find all those volumes? Formulas. All right, in calculus, how are we going to get these three-dimensional shapes? We haven't graphed anything three-dimensional, so this is where it gets a bit tough. All right, let's take some curve here. Some y equals f of x. And we're going to take that region that's in here. So this area that's underneath here, we're going to take that region and we are going to spin it about the x-axis. So this part up here kind of comes out and around and comes down and flips down through the page. So we're doing this. This is coming through and coming around this way. So this piece up here is going to come down there. And then this kind of comes around. To help you see that three-dimensional shape, we can kind of put ovals here at the end, just like we did ovals for an ellipse and a cone and a sphere. And if you darken this front edge here, this left edge, it'll make it appear like it's closer to you. And then we can kind of also show that we have a representative slice. So when we go through and we cut this up, we can put kind of a slice in here. And what that does is it helps you see the three dimensions. Do you see this coming out at you this way? And it's like a bell. It's like a bell shape. Do you see that coming out? Okay. All right, now how in the world are we going to figure out the volume of that shape? All right, so to do this, I'm going to find volume. And what happens is when we sliced this up here, we had all of our rectangles up there. When we sliced this, as we slice through, this has been spinning around. So we're going to slice through, we're going to get a circle. So we are going to add up a bunch of circles. Those areas, and then we're going to slice this up in tiny, tiny slices, and we're going to multiply each area by its thickness. And if you take area of something by how thick it is, that'll give you volume. A to B is going to be where we start chopping this thing up into little circles, and B is where we stop tracing it up. All right, now, what's the formula for area of a circle? Come on, area of a circle. Not 2 pi r, but pi r squared. So this would be the integral from A to B of pi r squared times thickness. Now your thickness is how wide this slice is right in here. Maybe you can think about it this way. It's a slice sitting like this. How wide is that slice? Well, we would measure across x horizontally, so that's an x thickness. So our thickness here is dx. That pi is a constant. You can pull that out. That leaves us with a radius in here. And if we look at this slice, this circle right here, there's your radius. There's the radius of that slice. That radius is a y value. So your radius is a y value. But we can't have y's and x's. Oh, but look, we know that y is f of x. that's it. It's not perfect, but is the general form for disk method. And it's a disk because it's solid. Oh, maybe I can do this. Yeah. Oh, I had an idea. Could you think of these as, like, can you see those coins stacked up? And we're going to take off a slice. That's a circle. And then we're going to find that area and then multiply by how thick it is. And then we do another one. And another one. And then this one's getting smaller because it's a little bit farther down. Okay. I don't know if that helped or hurt. I just had a thought, so I had to try it. All right, here we go. Find the volume of a cell. Let's take a look at an example, and if you're a little fuzzy right now, that's to be expected. Don't worry about it. Find the volume of the cell that's created when the region enclosed by x minus y equals 4, x equals 0, and y equals 0 is revolved about the x-axis. So we need to draw a picture and find out what this region is that we are revolving. So use color pencils. Grab some color pencils. It's going to help. Promise. Alright, this equation, x minus y equals 4. If I solve for y, it's going to be y equals x minus 4. Slope 1. There's that line. Y equals x minus 4. X equals 0. That's that line. And y equals 0. That. Alright, where's that region? Lightly shade that region in. That region, that triangular region. We're going to spin that about the x-axis, and the way that you show that spinning is right out here. We're going to take it from down here because it's underneath, and we're going to spin it up top. So this triangular piece comes and spins around this way, and it keeps going back through the paper the other way. What are we making when we spin that thing around? Yes, a triangle. Because when you spin it, we get a cone. Sure. Doesn't look three-dimensional right now. We're going to make it look three-dimensional. The way you make that look three-dimensional is you put an oval here, and here, darken this front edge, we revolved around the x-axis, so our slices, when we slice through, are going to be perpendicular to that axis of revolution. So put an oval in here. That shows a representative slice. One of those slices that were taken out, right there, that nickel. See that slice? It's sitting right in here like that. And there's going to be dimes over this way, and this is going to get bigger into quarters over this way. Okay. All right, let's find this volume. So, volume is a bunch of circles. So, pi r squared times thickness. All right, that pi can come out. That's a constant. Radius. Your radius, and you're always going to draw your radius, listen carefully, from the axis of revolution to the original function, down this way. That's the radius. Axis of revolution to the original function. Is that an x distance or a y distance right there? That's a vertical amount, so that's y. Excuse me, your radius then is y squared times thickness is how wide is that slice. And if you measure across this nickel here, you're going to measure in the horizontal distance, so that's an x value. So your thickness is dx. And we have a problem right here because we have y's and x's. But you know that y was x minus 4. So we can trade that out, x minus 4 squared dx. Bounds are going to be where you started slicing it up into circles until where you stopped slicing it up, where x is, so I want x bounds. So we start it at x is 0, we stop it at x is 4. Okay, your best bet here is to square that out. X squared minus an 8x plus a 16 dx. I'm going to save us some time. You can work through the antiderivative and the arithmetic there. Please make sure you can come up with 64 pi over 3. There's the volume. Make sure you can do that without a calculator, without FNINT, and without a calculator. Those numbers aren't that hard. Make sure you can come up with that. All right, let's take a look at this next one. Find the volume of the solid that's created when the region enclosed by y equals 2 square root x equals 1, y equals 0, and x equals 9 is revolved about the x-axis. Sketch a graph. All right, y equals 2 square root of x. Well, square root x does this. Look up here so you can see me draw it. Square root of x does that. 2 square root of x is just going to make it taller, so it's got that same basic shape. There's y equals 2 square root x. Okay, x equals 1. Y equals 0. Color pencils are probably showing up a little bit better for you than my pen because the pen's kind of going right on top of it. You're not seeing all the color. And then x equals 9. Out here somewhere. All right, we want the region that's bounded by all 4 of those. The region bounded by all 4. Is this bit. Why not this little triangular shape over here? Why not? Come on, come on, come on, come on. Somebody say it. Somebody knows. All right, I'll tell you if nobody said it. Because that one's not bounded by the x equals 9. It's only bounded by 3 of them. The 2 square root of x, the x equals 1, and the y equals 0. It's got to be bounded by all 4. That's the region. We are going to spin this about the x-axis. So we're going to take this thing, it's up here, and we're going to spin it around this way. So all of this up here is coming around down this way. All of this is coming around down here. So to draw it, just draw the reflection. Out here. and then put ovals on the ends. One here. That oval helps give that 3 dimensions. Let's pull it off. Anybody who's in art, you can probably do a beautiful job of sketching these. There we go. Oh, one more thing. We need a representative slice. You got to put one of those ovals or that slice in the middle. Okay. Here is what that is very much like. Oh, not this one. That is my cup. My Carl Sandburg cup. Do you see it? Yeah? Do you see that? Isn't that cool? All right. I think it's cool. Let's find the volume. All right, so volume is, we are going to add up a bunch of circles. So pi radius squared times thickness. Pi comes out. Your radius in your representative slice. The radius goes from the axis of revolution to the original function. There's your radius. That's a y value. That's a height. That's a y value. Y squared times, and then your thickness. How wide is that slice? You're measuring it dx. So if my hand was a slice, you're measuring horizontally across my hand. So that's a dx slice. They won't always be dx slices. All right. I can't have y's and x's, but we know that this y value is 2 square root of x. So we can 2 square root x squared dx, and bounds start to stop. Started at x is 1, stopped at x is 9. Okay? Square that out. That's 4x dx. All right, I will leave this to you to go through the antiderivative and the arithmetic and make sure you can come up with 160 pi. Make sure you can get that. All right, last one. Hopefully, I didn't time this. I don't know how long it is right now. Hopefully we have enough time. If we don't have enough time, then go please and watch this at home. You can search out the title. It's Calculus section 7.3. You can find it under my channel. All right, find the volume of the solid that's created when the region enclosed by x equals y squared, x equals 0, y equals 2, and y equals negative 2 is revolved about the y-axis. Sketch a graph. X equals y squared. That's y equals plus or minus square root x. This one? This one. There's x equals y squared. X equals 0. Y equals 2 and y equals negative 2. the region enclosed by those is this piece up here. And this piece down here. Okay. All right, let's take that region and let's spin it about the y-axis this time. This is going about the y-axis. All right, so to graph this then, it's going to spin around this way. Spin around this way. Copy it over this way. All right, now this one's kind of hard to imagine, and the best thing that I've been able to come up with is that this is kind of like a sit and spin. Do you remember when you were a little kid? There was a circle on the bottom you sat on, there was a circle on the top, and then you kind of turned your hands around the top circle and it made you spin around. Do you remember that? I hope so, because it was really fun. Okay. The other thing that maybe I can think of doing is if you take a water bottle and squeeze it in the middle. There, can you see? Oh, I'll pour water all over if I don't. Be careful here. Sorry, that's my family checking on me to see if I'm all right and see if I'm coming home because it's really, really late right now. Okay, so let's finish this one up and then I can go home. All right, so hopefully we can see this going on. If not, I'll have to talk to you about it when I get back. How do I want to draw this representative slice? Oh, I'll do orange. Representative slice. Right there. All right, find this volume. A bunch of circles. Pi r squared times thickness. Pi's coming out. Radius. From the axis of revolution to the original function. Hey, look at that radius this time. That's an x value. That's a horizontal distance. So that's x squared. Your thickness, your slices are running through this way this time. All those circles are coming through like this nickel, going up this way. So your thickness is dy. Oh, got a problem. X squared and a y. Got to change out that x squared. We know that x is y squared, so this is y squared squared. Okay, we need bounds. Start slicing, stop slicing. We start down here at -2, and we stopped up at +2. -2 to 2 of y to the 4th dy. Okay, one way to look at this. This is symmetric top to bottom. Do you see that the slices from -2 up to 0 are exactly the same as the slices from 0 to 2? So we could just find those slices from 0 to 2 of y to the 4th dy and then double it. Either way, please make sure you can come up with 64 pi over 5. Whew. All right, thank you very much. I hope to be here tomorrow. I just realized my paper was off the recording place. I hope you got everything.